Hi everyone. I'm working at Bull Atos in the data management team, and the subject today is about network layer in Lustre. So I will start with a brief summary of the LNet layer. So it's a communication infrastructure that allows communication between the clients and server Lustre nodes. Main features are to support different kinds of networks and allows routing between these networks. And the key features provided by LNet is that it ensures high availability and also recovery of the Lustre nodes, for example, through the multiple interface and router checker parameters, for example. And it's based on a modular implementation that allows to define and register a network driver for each kind of network that you want to support. And we introduced a new network support, which is called Portals4 LND, and it's based on the Portals4 specification made by Sandia National Laboratories. We developed the LND based or inspired from the deprecated Portals3 LND that existed several years before. So it's actually we already posted the new ID to the community code, and that allows us to define a new network name called PTLF. And in that kind of network, the adapter is identified with its device number, contrary to SOC LND or IB LND, where the identification is made with an IP address. And we got an implementation of the Portals4 specification with a Bull exascale interconnect hardware, which is the new hardware we provide to our customers. So I'm going to briefly present the Portals4 specification and its main features. So as I said, this is intended to networking communication between nodes and with high performance. So it provides a rich semantic that allows to implement both MPI communication, also a PCAS computing model, which is a partition global address space. It also ensures a full hardware offloading. So it means computing and networking is completely separated and can progress independently. It ensures connectionless protocol, so it means it's very scalable, since every number, whatever the number of nodes in the communication in the fabric, you got always the same footprint. And it's ensure reception of unexpected messages, so it's also a better optimization of the resources. So here is a summary of the main concept of the communication model for Portals4. So every node that implements Portals4 defines a communication endpoints through a portal entry, and this allows to be addressed using a network ID, a process ID, and also the portal index. And through that communication endpoint, the node exposes some portion of its memory regions. And this is defined with the match entry. And so you add the match entries to a list that is scanned when a message is received. So when a message is sent to that node on that portal with a specific match bit, the message is received on the memory region that is matched by the corresponding match bit. So let's have a look at how we are able to transfer a small data from node A to node B. So we have got prepared resources on the target node, which is on the overflow list with a persistent memory entry with a fixed match bit. And when a net layer calls LND, it provides a memory description of the data it wants to send through the LND send API. So the LND builds a message, and it includes the LNet header as its content. We then copy the payload, the LNet payload, into the message and send it using the fixed match bit to the node B. So we call that an immediate message. Since the fixed match bit is always provided with resources for reception, we've got a match entry that match that messages, and once it's matched, the LND calls back LNet so that the LNet header can be passed, and the LND received rule service is called back again to the LND by LNet, providing information on the LNet destination memory that allows the LND to copy the message payload into the destination memory for LNet. So there is a similar mechanism for the small message transfer as a get transfer. So let's have a look at the RDMA transfer. This is a rendezvous setup. So we start again with a pre-posted match entry on a fixed match bit. LND send is called by LNet, but we see that the size of the message requires or allows to perform a RDMA transfer. So the node A allocates a unique match bit and prepare a match entry on its side for the RDMA transfer, the bulk transfer later. Then it builds an immediate message to the node B, including LNet error and also the unique match bit. So this is sent as a rendezvous message to the node B, which is matched into the persistent match entry. Then LNet parses that header, identify the memory region for the destination, and call back LND receive. And that allows to prepare a memory descriptor on the node B side. And this memory descriptor is then allows to transfer with the PTLGet portal service the whole content of the bulk message using the unique match bit. And we've got this ensures the match of the prepared match entry on the node A, and so we've got a zero copy transfer from node A to node B. So once again, a similar transfer can be done for a get from node A to node B with simply the same kind of mechanism. So how do we use these Portals4 resources? On the reception resources, we only allocate one portal index, and we associate it an even queue so we can ensure asynchronous management of the events. And we have on the overflow list, we have several persistent match entries with the fixed match bit. So this allows to be able to receive dynamic transfer resource from other peers on the net, on the fabric. And so transmission resources are allocated through a transmission descriptor, immediate message and rendezvous messages, and there is also an event queue for transmission that allows asynchronous handling of the transmissions. We additionally use the priority list to handle the RDMA transfer. So these match entries and memory region are dynamically allocated thanks to the first rendezvous message. And this one are used once match entry. It means as soon as the match entry is matched, it's removed from the list. And this is the priority list is first scanned before the buffer list by the portal layer. And these unique dynamic match entries are matched with the transmission received from transmission resources of other nodes, with in turn uses bulk messages with a memory descriptor. So globally, the number of resources needed for communication is quite low, and this ensures a small memory footprint of the LND. So here are a few parameters and tuning that we can do with the new Portals4 LND. So we can control the number of concurrent transmission from a node to a dedicated peer, and from a node to all its peer. So this certainly allows to perform better with a higher bandwidth, but it consumes a little more resources. We can also configure checksum to check integrity of the immediate messages. And there is a parameter to control the number of scheduler threads that performs every kind of housekeeping task, like reset buffer reposting and transmission buffer finalizations. The LND provides certain debug and statistic information. For example, the number of events reserved and allocated, information on peers that is communicated to a net on demand, and also statistics on the number of transmission that has been performed. You find back in the right the kind of messages we've seen before. The put and get are the rendezvous setup messages. Immediate correspond to the immediate messages. No op is related to the credit management. Hello is related to the connection of peers. NAC is used to close the connection to a peer, and the bulk refers to the RDMA transmission. There is additional statistics that can be dumped to have information on the text descriptor state and the reception descriptors. So we have been able to perform a few performance measurements. The thin pink line, Portals4, indicates the current value bandwidth achieved at Portals4 layer with the hardware implementation. This is around 9.6 gigabytes per second, and it's still a work in progress. So we think we can gain a few megabytes, hundreds of megabytes again. And at the LNet self-test layer, we almost reached 9 gigabytes per second in read and 8.7 in write. We started working on the Lustre performance with that LNet layer, and globally we reach 8 gigabytes per second, and this is actually not really related to the network layer, but more related to our configuration. So what's next with this new LND? So we need some finalization for optimization and corner case handling. We also need to push the code to the master branch, so update our version to support the new 210 LNet features, and also interface changes due to the recent modification of LNet. And the goal is definitely to provide that code to the community, since it's based on a public specification. So I'm going to discuss some of the challenges we faced during the development of the LND. The first one is related to the LNet LND interface, which looks very simple and clear, with a registration routine and several function pointers we need to provide through a structure. So these function pointers are related to network interface startup and shutdown, control command for the IOCTL, send and receive services, as we've seen during the data transfer, and also LND queries and LND notification to get the peer, health, and aliveness from LNet or to LNet. There are also several LNet callbacks that are required to be called, and this looks simple, but looking in details, there are some shadow regions, or how can I say, unclear part of that interface. For example, what is exactly that LND, the exact list of services that LND should call to support callbacks to LNet, and some of the parameter description in the inline comments are not really explicit. I would like to mention, for example, the delayed parameter of the LND receive service. I thought initially that was related to the eager receive mechanism, but I faced some unexpected values of that field in the router configuration. So maybe I need to completely understand that field and then document it so it can be clear for this interface. Another challenge was related to the test. We got a LNet self-test suite, which is great for performance measurements, but it's quite hard to set up a new LND because we cannot perform a unique transfer or use memory descriptions that are not completely, that are unusual or exotic. So this leads us to develop a LNet test kernel module, which allows to specify reception memory buffers and also trigger data transfer with our own specification of the memory description to use. So this is probably something that could be helpful for everyone that wants to test or set up LND layer or LNet itself. And I will complete this talk with a discussion around opportunities that are offered by the modern interconnect specification. So here I am thinking about Portals4 at least, but also recent definitions of InfiniBand specification, or also open fabrics. At the moment, the LNet layer uses the RDMA services from that the RDMA feature from the network, but at least that's all. Even if modern interconnect provide much more features and rich features. So I'm going to suggest one or two kind of usage that we could use into Lustre and benefit for low latency and host bypass. So the first one is related to atomic operation. So what is an atomic operation provided by the network interface? It's a way to provide a memory variable managed by the network interface itself, and which is completely independently managed from the host. So every node of a fabric are able to update that variable atomically, and perform a set of operations on that. And the proposal is to make this kind of service available to upper layer of Lustre, like to Portal RPC, to enable, for example, distributed lock services, or maybe object sequence numbering, like for the file sequence number. Another suggestion would be to use the triggered operation. So this kind of operation is a way to launch a network operation conditioned by a number of messages received on a variable or on a memory region. In this example, we've got 3 layers of host, and we perform a reduction in a tree-based reduction. The first layer of host on the left is able to update the remote variable, and the second layer of host will then transmit the sum up value of the network variable into the lower layer, and this is triggered automatically without any control of the host. So this is quite this is very effective in terms of latency, and it does not involve the host at all. And one suggestion was to use that kind of mechanism to perform recovery synchronization, for example, in Lustre or any other ID. And I think that's it. Do you have any questions?
Thank you. Questions?
Portals4 has an implementation for InfiniBand verbs. Did you try that by accident?
Sorry?
There is a implementation, a driver in Portals4 for InfiniBand verbs. Did you try that to compare with BXI?
No, we didn't. Probably this is a user-learned implementation.
I think so.
Yeah. No, we didn't try that.
Does Portal4 semantics better match Lustre Portal semantics rather than other APIs?
Yes, that's a good remark. Actually, LNet implementation is based on the Portal3 concept, I think. So it's very similar at the LNet layer than the Portals4 specification we have used for the Portals4 LND. But I think we are not able to replace LNet layer globally with the Portals4 hardware implementation, if that's an idea, because we would lose all the features provided by LNet, like multiple network and advanced multi-rail, for example.
Other question?
As I see, you have introduced some atomic operations over LNets, but LNets have support for different types of portals. So operation should be supported over TCP network. How it will be work?
You're talking about the additional services I suggest to use?
Yes, if we have introduced new LNet IP, it should be supported by all LNDs on existing systems.
Yes, we could imagine to have this service optional, so only LNDs able to support them would be would register these function pointers, whereas old LNDs like SOC LND would not.
So this code can be used on generic Lustre code.
Yes, it could be used for optimized behavior.
So you should provide an ability to check this if this LND
Yeah,
supports.
certainly. Yeah.
But in most cases it will be too hard additional support to
I understand.
Okay, thank you, Gregoire.